The topic of this video is solving separable ordinary differential equations. And this lecture is drawn heavily from Greenberg's section 2.4. This is a section that you should be reading in conjunction with this video. What I'll talk about first is a definition of a separable equation, and then I'll show you how to rearrange them so they can be solved using integration. I'll give a very simple example, and then I'll cover Greenberg's example of a nonlinear ODE pertaining to population dynamics. From this video and the problem set you'll work on, you will gain a knowledge of how to recognize a separable ODE, and then how to solve both linear as well as some nonlinear cases. Now, many times, or in some cases, an ODE can be expressed with the derivative of the desired function on the left-hand side and some function of the independent and dependent variable on the right-hand side. Now, if f of f can be rearranged into the product of two separate functions, one function, capital X, being only a function of the independent variable, and the other function, which I'll denote as capital Y, as being a function of the dependent variable, then the equation is separable. Again, capital X only depends on X, and capital Y, the function, only depends on the dependent variable, which is what we seek. And this is a separable equation. And it's relatively easy to solve because we can break up the derivative in terms of the differential on y and put the function of y on the left-hand side and set that equal to capital X times dx and integrate both sides. The first case in which we looked at this was the linear non-homogeneous case, which we showed was separable, but more complicated equations can also be separable. So this is the definition of a separable equation, and to recognize them, you just need to recognize that you can break this right-hand side in terms of the product of two functions, only dependent on X, and the other only dependent on Y. So the first example is also covered by Greenberg, is the solution to dy dx is equal to y squared. So this is a differential equation. It happens to be a nonlinear ODE. It's first order because we have a first derivative, and the nonlinearity comes in because we have y squared. It's separable because we have only a function of y times the product of 1, which is the function of x in this case. And so we can solve this by bringing all the terms of y on the left-hand side and all the terms of x on the right-hand side and integrating. And when we do that, we find that we get minus y to the minus 1 is equal to, oh, I'm sorry, the example had a minus y on the right-hand side. Okay, forgetting that minus. And so we have a minus, the integral of dx is x, and then we have to have our integration constant. So our solution is y is equal to positive 1 over x plus c. Now suppose we are given an initial condition that y at x equals a is equal to b. And let's say, for example, a is equal to 0, so this is our initial condition, and b is equal to, say, y naught. So the initial condition is y of 0 is equal to y naught. And so we substitute this value in for y and 0 in for x to solve for our constant, and we get that our constant is equal to 1 over y0. And then our particular solution with that initial condition is y is equal to 1 over x plus 1 over y0. And we can write this in a slightly different form, just doing a little bit of algebra. Y naught over the sum of x times y naught plus 1. Okay, so that was a relatively simple example. And in this case, again, this was a nonlinear ODE. So let's look at something a bit more interesting. Let's look at a case of population dynamics. This was also covered in the previous section. But you might imagine that if we have, say, n is the number of individuals in a population, they could be microbes in a microbial system. They could be people in a country or something like that. But you can imagine that the rate growth of that population, the rate change in n, the number, well, could be proportional to the number of individuals there are present, right? The rate of productivity depends on the size of the population. And our population growth parameter is, I should write kappa to be consistent. So kappa is the controls the growth rate right? So if kappa is less than 0, then the population is declining. Or where if kappa is greater than 0, then the population is growing. So I hope it's intuitive that the rate of population growth depends on the number of individuals there are to grow the population. So this is a homogeneous linear ODE, and we saw this equation when we looked at radioactive decay. But as you might recall, the solution was an exponential growth rate. It was proportional to e to the kappa t. But you can imagine that population, this may be somewhat unrealistic, and that the population could not grow forever, assuming kappa is positive, because there are other factors, environmental factors, that might limit the rate of growth if the population gets too large. So you might imagine that the limits on population growth might also depend on how large the population is. Now, the Verhulst population model asserts that the growth rate, kappa, is equal to some constant minus some constant times the population size itself. So when the population is very small, the growth rate is very large. But as the population grows, the growth rate decreases linearly with the population. So let's insert this function for kappa in our differential equation. So we have our growth rate again on the left-hand side is equal to our growth rate parameter. This is our growth rate parameter, kappa. That's a minus b times n. And again, the growth rate is also proportional to n because it depends on the number of individuals there are to reproduce. So as long as if a is greater than b times n, then kappa is positive, and the population will grow. But at the limit, when b times n equals a, or the limit when n approaches a over b, then dn dt approaches 0, it goes to 0. So you should recognize that this is a separable equation because we have a derivative on the left-hand side, and functions, we have a function of only n times a function of our independent variable t, which happens to be 1 here. So we can collect all terms of n on the left-hand side. We have the differential of n divided by a minus bn times n, and that's equal to dt. And we can solve this by integration. The other thing I'd like to also point out, this too is a nonlinear ODE because we have a product of n with itself as one of the terms. So we can use this method. Because it's separable, we have some relatively simple techniques for solving even a nonlinear system. So our task now is to solve the integral on the left-hand side, and you can see it's a somewhat complicated function of n because we have a quadratic function of n in the numerator. But you can imagine this integral would be easier to solve we could more readily solve the left-hand side if we could write the denominator this term a minus b n times n in terms of the sum of partial fractions. So that has the form of a, some constant, over a minus b times n, the first function of n, plus b over n. So these are partial fractions. And so if we could do this, we would have two separate integrals, one only as a function of a minus b over times n, and one is a function of 1 over n. So to do this, we have to solve for these coefficients a and b. So let's do that. Okay, so to do that, we would carry out this summation by doing what we learned in the past, is we find the common denominator by multiplying the denominator would be the product of the denominators of these two fractions. But to do that, we have to multiply a times n, and then b times a minus b times n. So expressing, so we have to write this, so we have to find the common denominator. And so we have a over little a minus b times n plus b over n is equal to a times n plus b times a minus b times n over the products of the two denominators. Okay, so that's what we know, and this is equal to 1 over, we want to solve a and capital A and B such that it's equal to 1 over the product of a minus b n times n. And so for this to be true, the numerator here must equal 1. A times, I'm going to collect terms that are products of n, so we have a minus big B times little b times n plus big B times a. That has to be 1. So this again is the numerator just rearranged to collect terms proportional to n. The numerator is equal to 1. And for this to be true, since the right-hand side is not a function of n, then that must mean that a minus big B times little b is equal to 0. And that must also mean that b times a is equal to 1. Because again, remember, big A and big B are constants. They're not functions of n. And so we have two equations to solve for two unknowns. And the unknowns are capital A and B. So the second of those two equations gives B is equal to 1 over A. And when we substitute B, 1 over A, in for B in the first, we get A is equal to B, little b, over A. So we've solved for the two coefficients that allows us to break this fraction into the sum of two partial fractions. And therefore, the left-hand side is the integral of b over a, that's what a was, over little a minus b times n, plus 1 over a over n, all times dn. And we can break that into two separate integrals, which is b over a over little a minus bn times n dn, plus the integral of 1 over a over n dn. And let me switch to the other side. So in the denominator of the first integral, I'm going to factor out a 1 over b. So we get a b over a times a 1 over b times a over little b minus n dn plus 1 over a times the integral of 1 over n dn. Sorry, I'm factoring out a b in the denominator, not a 1 over b. Because when I did that wrong. So this should be b. And so when we multiply this through, we get a minus b times n, which is what we started with. And so the b on the denominator cancels with the b in the numerator. And this gives us 1 over a times our two integrals, which is, I'm going to write the first integral first, so that's dn over n, and then I'm going to rearrange the denominators, multiply by minus 1 basically, the numerator and denominator by minus 1. So I'll switch the order of the difference in the denominator and carry that out to minus 1 at the very front. Okay, and when we do this, we can solve the integral now. We get 1 over a times the log of the absolute value of n minus the log of the absolute value of n minus a over b. And the difference of logs is equal to the log of the quotient. So we get n over absolute value of n over the absolute value of n minus a over b. And now let's go back to so we started off with this left-hand side is equal to the integral of dt. So now we're ready to solve our differential equation. So we've solved the integral of our left-hand side. Now we have to equate that with the integral of dt, which is just t plus an integration constant. And so this tells us that the absolute value of n over n minus a over b raised to the 1 over a power. Remember, we're going to take e raised to the left-hand side and the right-hand side. And that equals e to the t plus c. And just doing a little bit more algebra. Our constant turns into a product of e raised to the a now, because we've raised everything to the a power to get rid of the 1 over a on the left-hand side. And again, our constant turns into a product. Our constant term here turns to a product with e raised to the at power. And now we can remove the absolute value sign and say that a can be either positive or minus b. So we get the solution being n over n minus a over b is equal to a e to the at. So that is our general solution to the Verhulst population dynamics model. Or rather, I should say that this gives us, from this equation, we can obtain the solution because we just have to rearrange it to solve for n. But before we do that, let's define our initial condition. So our initial condition is that the population at time is equal to 0 is some specified value, n0. And so with this, we know that n naught over n naught minus a over b is equal to a, because when we substitute 0 in for t, e to the 0 power becomes 1. And again, we substitute n naught for our initial condition. So this gives us the value of our constant, A. And so from that, we get that n over n minus little a over little b is equal to n naught over n naught minus a over b times e to the at. And now solving for n, if we do a little bit of algebra, we find that n is equal to a n naught, little a over times n naught, all over a minus n naught times b e to the minus at plus n naught b. And that is our solution, with our initial condition being defined at, again, at t is equal to 0. This is our final solution. Okay, and I wanted to just plot this up, and I used MATLAB to do that. So I wrote this little MATLAB code that evaluates this solution for different values of a and b. And when I run that code, here's the population growth that this model predicts. So my initial population was a million. This, I believe it's a million. Yeah, 10 to the 6. That's n naught. And I allowed time to range for a certain amount of time. And the solid curve is for, say, a reference value of b relative to a times, well, reference of b relative to a. For a greater initial growth rate, we get this curve, and for a smaller initial growth rate, we get this curve. And you can see that as you might predict, that when the growth rate, as predicted, the growth rate starts off as being high, but eventually the growth rate tapers off and flattens off after a long time. And that's because if we look back at our original equation, where was that? That's right here, right? The rate of growth is equal to kappa, which is a function of n, times the population itself. And if we let me go ahead and look at this together with this equation. So remember, kappa started off being maximal because when the population was minimal, and that's seen by this steep growth rate. But eventually, as external pressures limit the rate at which population can grow, as simulated by this n-dependent kappa, the population tapered off and stabilized at a certain value. Okay, so this concludes my presentation of population dynamics as a nonlinear ODE, and we solved it by recognizing that this ODE was separable.